Hey folks, welcome back on the concluding video on transpose of a matrix. In the previous two videos, I explained you the geometric intuition, if you remember all these things, on what does it mean to talk about transpose of a matrix, how you should think and intuitively think about that. But that was for folks who were really interested to know the subject and just get some intuition and sense of understanding before they proceed. But this video is purely for folks who don't really care, who just want to understand and get the basic marks and keep moving. Okay, this is for those folks. Like I said, it's clear my paper. Folks who want to clear the paper, just focus on this. You can skip the two videos before this. Okay. So what is the transpose of a matrix and what is the boring definition that textbooks define, or if you open up any textbooks, you'll pretty much see that this is how they open up. Transpose of a matrix is nothing but interchange of rows and columns, right? Whatever rows and columns you have, suppose there's a matrix given to you, right? And you have rows and columns. This is row 1 and this is row 2, and this is column 1 and column 2 and column 3. If you interchange them, it becomes a transpose, a transposition of the matrix. Basically, row becomes column and columns becomes the rows, right? That's what it is, right? For example, if you see here, the first row is 1 2 3 4, and if you see this matrix, this first row has become the first column here. 1 2 3 4, the row and column have been interchanged, right? And the transpose of a matrix is usually denoted by a capital letter A or any matrix in letter A with kind of a, it's not a power, but it's put in the power position T for transpose. It's just a way of denoting it. Or sometimes they might also use like A and kind of a single closing quotes or A prime. Both are like the same. So if in the exam they ask you find this or this, basically they're asking you to find the transpose of the given matrix. See over here, this is the transpose. This is the original matrix and this is the transpose, or vice versa, doesn't matter because it's the same thing. And what in essence it happens, right? You're basically interchanging the rows and columns. So the order of the matrix is going to be interchanged. This is a 4 by 3 matrix, right? Sorry, this is what, okay, this is a 3 by 4 matrix, right? Okay. So this is, let's take this example. There are 4 rows here. Row 1, row 2, row 3 and row 4. So 4 rows, 4 by 3, because it has got 3 columns, 1 2 and 3. And if you want to apply the transpose of the matrix, where you're going to simply make the rows into columns and vice versa, you get this matrix, which is a transpose. And if you see the order of this matrix, this has become a 3 by 4, the exact opposite, right? The number of rows and columns are interchanged over here, right? That's what it is. So that's kind of the algebraic definition of transpose of a matrix. And you just need to know that from exam point of view, unless you want to know the intuition behind that. And some of the examples over here are, for example, let's say I'm creating an Excel file, and in Excel file there is a function called as transpose. So if you see here, these are the rows in the direction of the x-axis, and if I apply the Excel function transpose on this, the rows and columns, the rows become columns and the columns become row. For example, if you see, the row 1 is country, grapefruit, lemons and oranges, and this is what it has become, right? And the same way each row has become a column. All these things I copied from Google, just letting you know. And a more kind of a transparent definition of, if this is a matrix and these are the elements A minus B, A this thing, and if its transpose is, this row becomes this column, okay, and this row kind of becomes this column. That's what it means. Similarly, for a 3 by 3 matrix, the same thing. The first row becomes the first column. That's what it means, right? And here are the same examples with numbers, and in this case I've taken square matrix. Transpose of a matrix could be for a square matrix or for a rectangular matrix. For example, over here if you see, it was a rectangular matrix where the rows and columns were not same. It could happen. And in this case it's a square matrix. In the square matrix, there is another kind of a way to think about that is, let's say if this is the matrix A and the transpose A to the power T, but it's not a power but AT is given as, the rows here become the columns and the row here becomes the second column, or vice versa. If this was A, this would have become AT, right? Similarly over here, right? This is the input and this is the output. If this is A, this is AT, transpose of a matrix, right? Where the rows and column are interchanged. And another way of looking at that is just for the square matrix, not for the rectangular matrix. In rectangular matrix also it's true, but I'll come to that in a minute. For square matrix, you can also think that if you just draw a diagonal where you have equal number of elements, diagonal as in a kind of a backslash diagonal, starting from the leftmost corner on the top to the rightmost on the bottom, and which makes, in case of a square matrix, then in that case, if you draw a diagonal for a square matrix, there will be equal number of elements, data elements on both the side. Over here you have 1, 2, 3, and you have 1, 2, 3. So what a transpose primarily does is it is as if you're placing a mirror across the diagonal on this case, and since the elements are exchanged, it looks like a reflection across the diagonal axis. The mirror is on the diagonal, right? This is what it shows. This pink color is the mirror, and the dotted is the mirror over here, and the pink color is kind of the reflection, right? So if you see, the 4, 7, 8 have moved here, 4, 7, 8, and 2, 3, 6, which is kind of in the upper section, has moved here. That's another way of looking at that. Even for rectangular matrix, it may not be a pure play reflection, but it always maintains the diagonal never moves the position. If you see, 1 and 6 are in diagonal position. Over here also 1 and 6 are in diagonal position. So any two or more elements which are on the same diagonal, right, they don't seem to change the place, right? The other elements kind of keep moving around. So if you take the relative positioning on this left matrix, on the right matrix, between two elements which are diagonally connected, that relativity is still maintained on the transpose matrix. So in case of rectangle, you can think about that. In terms of square matrix, it will be a whole reflection, complete reflection, because of the symmetry. The number of elements are same on both the side, and it can be complete reflection of the data elements moving up and down. It's like just a fun fact of how should you think about that, right? So that's all you need to know from the exam standpoint of view. And in the next session or video, we'll just solve a couple of examples, specifically exam problems on transpose of a matrix. Not a big deal, as long as you remember the rows and columns are interchanged. That's all, guys. The algebraic definition of transpose, short video, and I'll see you in the next video. Thank you.